Okay, how's that? Good? Okay. Great, so thank you. So I'm Erin Kado-Fong. I'm a graduate student at Princeton, and I'll be continuing our mini section on tidal features and why we care about these, hard to find, hard to measure, hard to characterize tidal fluff. So, comme soir, I did a good job of talking about why we care about tidal features, but just to reiterate, mergers are a critical mechanism in galaxy assembly, both for growing stellar mass. So here's just a plot from illustrious stellar mass versus ex situ mass fraction. And it increases as stellar mass increases until the most massive galaxies are dominated by ex situ mass. And it's also important, mergers are also important for building structure. So here's a halo from Bullock and Johnston with just a ton of substructure. And a bit about the two-stage formation mechanism of redshift 0 massive ellipticals, wherein dry minor mergers build up these accreted outskirts. So tidal features give us access to ongoing accretion events. And the Hyper Suprime-Cam Subaru strategic program is especially well suited for searches for low surface brightness objects. And Song and Johnny have already talked a bit about what's so great about HSC, but just to reiterate, HSC will eventually cover about 1,400 square degrees to an I-band limiting depth of 26 magnitudes, and it will be in 5 optical bands. It's composed of 3 layers, but today I'll just be talking about the wide layer. And I think Johnny's already beat up a little bit on SDSS, showing the comparison images, but to do that one more time, here's a SDSS SteerEye color composite, and here's HSC. Is there a way to turn the lights down a bit? As you can see in HSC, this nice disrupting satellite galaxy pops out. Awesome, thank you. And you can see it here in the color composite image. So this is just done with the first 200 square degrees of the HSC wideband. But even starting from there, we don't want to look at every galaxy in HSC because that will eventually be unfeasible sample. So right now we're starting with the SDSX spectroscopic sample, which is about 21,000 galaxies. And we identify tidal features automatically using what can essentially be thought of as iterative unsharp masking with thresholding. So here is a simulated tidal feature from Hendel and Johnston overlaid with a non-interacting, no tidal features smooth HSC galaxy. This middle panel is the detection map, so it's essentially what the algorithm sees. And the shells pop out here. And on the right is the simulated Hendel and Johnston shell. The orange contours, both in the simulation and this HSC galaxy up here, show the detected regions that the algorithm says are tidal features. So for this initial application, we also visually classify the tidal features as stream-like or shell-like. And I'll talk a little bit about that in the next slide and remove some false detections due to imaging artifacts. So this leaves us with a sample of about 1,200 HSC galaxies that host tidal feature systems from our SPECSY parent sample. And they're classified as stream-like. Here's an HSC stream on the left and a Hendel and Johnston stream down below, or shell-like. And here's the same HSC and simulation. And the reason that we do that is because stream-like and shell-like morphologies generally correspond to the angular momentum of the satellite during infall. So we can use this to see if the streams and shell populations show different characteristics. So the easiest thing to start with is the place that has the most light up in the host galaxies. And we find that shells are preferentially found around massive ellipticals. So here is the host stellar mass versus the fraction of tidal features that are shells. And it rises pretty monotonically towards higher masses. And this was expected already from simulations by, for example, by Zhang et al. In 2013, that more massive galaxies experience more radial satellite infalls. Here on the right is G-I color versus concentration, which we're using as a rough proxy for morphology. The gray points here are the full parent sample. The blue are the stream hosts, and the red are the shell hosts. So the shells occupy the more ETG type area. So then for a subset of our tidal features, they're sufficiently offset from their host galaxies that we can measure an independent color for the tidal feature and for the host galaxy. So here's the G-I rest frame color distributions of the shells in red and the streams in blue. And you can see that the shells tend to be redder than the streams. And some of the streams, the rest frame colors, are blue enough to host star formation, whereas the shells are largely consistent with red sequence satellite progenitors. And this is particularly interesting for the shells because for red sequence mergers, we can constrain the mass ratio from the color difference between the tidal feature and the host galaxy. So here, I've taken another schematic from Song, but if you have a merger in which both the infalling satellite and the host galaxy are on the red sequence, you can use the difference between their colors to trace back their mass ratio. And here is our distribution of differences between the G-I tidal feature color and the host color. And it peaks around -0.2, meaning that the tidal features are on average bluer than their hosts. And this corresponds to a mass ratio of around 4:1 or 10:1. But there is a significant subpopulation of tidal features that are as red as their hosts, indicating a more major merger origin. And we looked into this because there have recently been results from Illustris, from Roxana Pop's work, that indicate that most shells actually come from this major merger scenario, rather than the canonical minor merger, in which a satellite falls radially into the potential of the host. And indeed, we find about 15% of our galaxies can be thought of as coming from major mergers, and the remaining sample comes from minor mergers. And we also find that the major merger shells are much more likely to be aligned with the major axis of the host. About 86% are these quote-unquote type 1 shells, in which the shell caustics are stacked up along the major axis, whereas only about 30% of our minor merger shells are these type 1 shells. Most of them have caustics that are oriented more randomly about the host galaxy. And this is also predicted from the Illustris major merger shells. Most of them are these type 1 shell galaxies. So just to fulfill the second part of my talk in my last few minutes, HSC is also well suited to access dwarf-dwarf mergers. So if you look at predictions from SDSS, only a few % of low Z isolated dwarfs are expected to be dwarf multiples, to have a companion dwarf of similar mass, on the order of 2 to 4%. So you really need depth, resolution, and area to extend this low surface brightness dwarf-dwarf merger feature sample. So here on the left again is SDSS little blue blob, and on the right in HSC, you can see that significant tidal features pop out. And there's already been some very nice work that came out recently on this using SDSS and the Legacy Survey from Tidal 2018. And just to give some short preliminary results from the dwarf-dwarf mergers. So you can think of shells as a product of a merger between two dwarfs due to their morphology. And here's a small sample of 4 shells between dwarf-dwarf galaxies, or 4 shells formed by dwarf-dwarf mergers. And you can see, first, that the shells have blue optical colors. So here's the G-I rest frame distribution between massive shells in gray and color-coded dwarf shells here. And that that there is evidence of triggered star formation, especially in this case here, where there's a star formation aligned with the stalk of the shell umbrella. And this is all indicative of the idea that shells around massive galaxies form from minor mergers generally with small red sequence satellites, whereas shells from dwarf-dwarf mergers are formed from mergers between 2 gas-rich field dwarfs. So just to summarize, we searched through the SDSS spectroscopic sample in the first 200 square degrees of HSC to find 1,200 tidal feature hosts. We see that some streams show evidence of ongoing star formation, but shells are largely consistent with a red sequence minor merger origin, though there is evidence for a major merger origin for about 15% of the shells. And we also see shells around dwarf galaxies, which is evidence of field dwarf merging. And I'll leave it there. Thank you.
Some questions? Sure.
Well, I think that the idea is that the shells are formed at the end state of the merger where the cores are oscillating. So it ends up that the shells are thrown off along what will eventually become the major axis.
Have you tried to study the observational timescale? As discussed earlier, Mark asked the question to Thomas. What is to convert data to show these number counts in some area of the sky over some redshift range into rate, either per galaxy or per cubic parsec? You need to have the observability timescale. So that's a crucial aspect of doing these kinds of studies.
Right. So I think what threw a wrench into thinking about this is that we discovered that some of the shells come from major mergers. And right now, there isn't a simulation that has both shells from major mergers and minor mergers. So we don't have a consistent idea of the observability timescale for this. We use the colors of the shells as compared to the color of the host. Right. Right, so we looked at the effect of, so in the lustrous galaxies, they also looked at the metallicity of the shells versus the hosts. And that would predict that we would, within our errors, see the same colors. And we also looked at the effect of stripping off the outskirts, and it shouldn't be large enough to mimic the signal. Yeah, I think that the number one thing that we would want to do is create a classification scheme that's continuous and that can be applied to both observations and simulations. Because one thing that we've been running into a lot is that different people have different ideas of shells and streams, and it's not really a bimodal classification, it's just a smooth continuum. So I think before we think about the nitty-gritty, like opening angles of the shells and the surface brightness evolution, we want to at least be talking about the same thing when we say shells and streams.
Okay, let's thank Erin again.